Welcome to module number 8. I'm going to make two very short little videos. It's easier for me to upload that way. So the first part's going to be just on potential energy diagrams. And this actually is a really important little concept. You will see this again next year at university for sure. You'll see them in biology, you'll see them in chemistry, you'll see them in physics. Okay? So in chemistry, we took a look at a chemical reaction where we look at the amount of energy in total that are in the reactant bonds, if you will, right? In total, how much energy do the reactants have? And then we're going to look at how much energy in total the products have. We're going to graph them to show the potential energy over just the reaction coordinates, okay? So you can see on this little diagram right here, basically you're just going to have two lines. And are those lines going to have the reactants lower than the products, or are those lines going to have the reactants higher than the products? Okay, and that's just going to be the difference between whether this chemical reaction is an endothermic reaction or whether it's an exothermic reaction. So remember that energy changes within a system, okay? And because of those forming and breaking bonds, those intramolecular bonds, that's basically what we're looking at. So always, when your intramolecular bonds are broken, energy is absorbed. And always when new bonds are formed, energy is released. But we're just going to look at, all right, how much total energy does that take in the absorbing and releasing? And then compare those two values, and you can simply do it on a potential energy graph. Okay, so here we go. Figure number 1. I know there's a lot on here, but basically this just shows you that we have an endothermic reaction here. So for example, dissolving salts and photosynthesis. Can you see that the enthalpy difference between these two, okay, going in the forward direction, we would take the amount of energy that the products have, which is translated to 15 kilojoules, take that away from the amount of energy of the reactants, that's 10 kilojoules, all right, and your total enthalpy of this reaction is 5 kilojoules. So is this reaction endothermic or exothermic? Well, when you take your products, take away your reactants, you have a positive value. So that tells you that you've got an endothermic reaction. Okay, now, is this the whole case? No, not necessarily. That brings us to figure number 2. Figure number 2 shows you what it would look like with a reaction where you've added in the energy of activation. Okay, that's an important term. What is the energy of activation? It's the amount of energy required for the reaction to take place. Okay, so you know that if you've got propane sitting there and you've got oxygen sitting in a room, it's just not naturally going to spontaneously combust. It needs a little bit of energy to get it kick-started. That amount of energy that it requires to go over the hump to get the reaction going is the amount of energy required, which is the energy of activation. Okay, so you can see here on the diagram that if we've got the amount of energy of the reactant same as 10, products was 15 kilojoules, the enthalpy in the forward direction, 5 kilojoules, that's exact same as the figure above, but now you can see that this reaction needs to apply a little bit more energy in order to get that reaction going. That's the energy of activation. So this reads as the energy of activation in the forward direction would be 25, take away 10, those come right from your graph, 15 kilojoules of energy required. Okay, that's the energy of activation. And how would that look as a thermochemical reaction? Would it be the 15 kilojoules of energy plus the reactants to give us the products? Or would it just be the 5 kilojoules? Well, this is your right answer right here. Okay, it would only be the difference between the products and the reactants as the enthalpy needed. Okay, will the reaction take place? It still needs to have the amount of energy that it needs for that reaction to get kick-started, and that's the energy of activation. Okay, what happens? Well, at the molecular level, you're thinking, I can see my reactant particles and I can see my product particles together at that exact moment that that reaction is going to take place. You have intramolecular bonds being broken, new intramolecular bonds being formed between the new atoms, and that complex is called the activated complex. It's a high energy, unstable intermediate formed during a reaction. The intramolecular bonds simultaneously breaking in the reactants and forming in the products. Okay, so that's your example right here. They've shown you what the activated complex could look like if you had a reaction where you've got hydrogen gas burning with oxygen gas and producing water. Okay, so you can see what that energy activated complex might look like. All right, last thing here, you can see this is an exothermic reaction. How do I know that? Well, the enthalpy in the forward direction, that's the little F beside the delta H, would be the products. Take away the total amount of energy in the reactants. So I'm looking at 100, take away 340 gives me negative 240. That's my indicator that this is an exothermic reaction. Okay, can you see here the energy of activation going in the forward direction? As is, my reactants and the products would need to get over this hump. That's that value right there. Okay, and you can just take your value 440, take away 340. If you were to reverse this reaction and you wanted to take water and split it up into hydrogen gas and oxygen gas, could you do that? How much energy would it take to do that? You'd start way down here, go all the way up. That shows you the energy of activation in the reverse direction, and that's what that would look like. So those are the different values you can get from using a potential energy diagram. Okay, that's it for now. Do the back page, check my solutions. It gives you a practice question, and I'll meet you for part number 2.